Welcome back to the deep dive. Today we are looking up, and I don't mean just, glancing at the sky while you walk to your car.
Yeah, no.
We are talking about a fundamental shift in perspective. We are shedding the gravity of our daily routine and trying to wrap our heads around something that is famously difficult for the human brain to process.
It is the ultimate challenge, isn't it? Our brains are wired to understand distances we can walk or maybe drive.
Right. Things on a human scale.
Exactly. We understand temperatures that might make us shiver or sweat. But today, we are diving into space, a visual encyclopedia. And, the first thing this source makes absolutely clear is that our intuition, our common sense, it's completely useless up there.
Completely useless. And, when I first saw the title encyclopedia, I had this flashback to fourth grade.
Oh, yeah. The dusty books.
I was expecting lists of dates, maybe some dry facts about rock densities, but this material is, well, it's aggressive. It frames the conversation not as a science lesson, but more like a survival guide for a journey.
A survival guide. That's a great way to put it.
A journey from the surface of our small blue planet, as they call it, to the absolute edge of what we can see.
That's the right frame, because space isn't just a place. It's an environment. And it is a hostile one.
Unbelievably hostile.
It's a vacuum filled with radiation, extreme temperatures, and violence on a scale that makes our worst natural disasters look like a hiccup.
That's the hook that really got me. We tend to romanticize the stars. We think of peace and silence and floating.
Tranquility.
Yeah, exactly. But the source just keeps emphasizing the violence, exploding stars, freezing voids, speeds that turn little dust motes into bullets.
Precisely. And so I think our mission today is to navigate that violence. We're going to extract the most mind-bending facts, sure, but I want to focus on the mechanics. How do we actually know what we know?
Right, the how.
How do we survive the vacuum? And why is Mars, our rusty little neighbor, such a complicated and frankly dangerous destination?
So let's start at the beginning, or rather, let's start at the edge. Section 1, what actually is space?
It sounds like such a simple question.
It does, but looking at the source, the answer is surprisingly messy. I think most people have this mental model where, you get in a rocket, you fly up, and at some point you hear a pop, the sky turns black, and you are officially in space.
Right, like crossing a state line, there's a big sign that says, "Welcome to space."
Exactly. We want a border. We want a wall.
But nature doesn't really do hard borders. The atmosphere doesn't just end, it fades. It's a gradient. The air just gets thinner and thinner and thinner the higher you go.
So it just kind of trails off.
It does. But traces of Earth's atmosphere hang around for a very, very long time.
I mean, for legal reasons, for treaties, for awarding astronaut wings, we have to draw a line somewhere. You can't have a vibe-based border for space.
No, you can't, hey? You do need a definition. And the source points to the Kármán line. This is the internationally, or at least generally, accepted boundary.
The Kármán line. Okay, and how high up is that?
It's at 62 miles, or 100 kilometers above sea level.
62 miles? That feels, I don't know, suspiciously low. I mean, my commute is longer than that some days. If space is that close, why is it such a monumental engineering challenge to get there?
Oh.
It feels like we're missing a variable if it's just like a 1-hour drive straight up.
And you've just hit on the single most common misconception in space travel. You are confusing altitude with orbit.
Okay, break that down.
Getting to the altitude of space is actually, it's relatively trivial. The V-2 rockets in World War II could touch the edge of space and come back down.
Wow, really? Back then?
Oh, yeah. The problem isn't going up, it's staying there.
Because of gravity just pulling you right back down.
It's all about speed. See, the Kármán line isn't just an arbitrary number. It's derived from physics.
Yeah.
A physicist named Theodor von Kármán, he calculated that at roughly that altitude, the atmosphere becomes so thin that for an aircraft, like a plane with wings, to generate enough aerodynamic lift to stay up, it would have to fly faster than orbital velocity.
Wait, okay, let me process that. So the air is so thin that to get any lift from your wings, you have to be going so incredibly fast.
So fast.
That you're basically becoming a satellite anyway.
That's it, exactly. At that point, wings and aerodynamics stop mattering, and orbital mechanics completely takes over. So that's why we draw the line there. It's the point where flying ends and orbiting begins.
So in the U.S., if you fly above that 60-mile line, you earn official astronaut wings.
That's the rule.
But strictly speaking, you could get those just by, jumping really high for a few minutes and then falling back down.
Technically, yes. That's exactly what suborbital flights do. You see it with space tourism companies. They punch through that ceiling. You get to float for maybe 4 or 5 minutes in the blackness, see the curve of the Earth,
And then you just fall.
and you fall right back down. You touch space, but you don't stay in space.
But here's where the source material surprised me. Even if you cross that 62-mile line, you aren't totally free of Earth. We think of space as a perfect vacuum, but there's still stuff there.
Oh, there is. We call it the exosphere. It's the very outermost, whisper-thin layer of our atmosphere, and it extends way, way up to 6,000 miles high.
6,000 miles. That's incredible.
Yeah, it's incredibly thin. I mean, by any laboratory standard on Earth, it's a vacuum. But there is still hydrogen and helium atoms floating around, leftovers from our atmosphere.
And the source describes something happening in the exosphere that I found slightly unsettling. It says Earth is leaking.
It is. It's a process called Jeans escape, named after the physicist James Jeans. Basically, in that super high, super thin upper layer, some gas molecules get zapped by solar radiation.
Like a little kick of energy.
A big kick of energy, enough to just drift off. They achieve escape velocity and just float away into the void. We're slowly, constantly bleeding a tiny bit of our atmosphere into space.
That sounds like a problem. Should we be worried about that? Are we going to run out of air?
Yeah, no, not on any time scale that matters to human civilization.
Yeah.
It's a very, very slow leak. The magnetic field protects most of it. But it's a good reminder that our planet isn't a sealed Tupperware container. We are open to the cosmos.
Okay, so you pass through the exosphere and now you are in the deep void. The environment changes drastically. The first thing, obviously, is the blackness.
The visual change is stark. It's profound.
But why? I mean, the sun is still up there. It's brighter than ever because there are no clouds, no atmosphere to dim it. On Earth, when the sun is out, the sky is blue. Why isn't space blue? Or at least white?
It all comes down to matter, or more specifically, the lack of it. Here on Earth, we are living at the bottom of a thick soup of atmosphere.
An ocean of air.
An ocean of air. And when sunlight hits those nitrogen and oxygen molecules, it scatters. It bounces around like a pinball. Specifically, the blue wavelength of light scatters the most.
Right, that's why the sky is blue.
That scattering creates the glowing blue canopy we see. It looks like the light is coming from everywhere at once.
So the blue sky is just lit up air.
That's a perfect way to put it. In space, there's nothing to scatter the light. It's a near-perfect vacuum. The photons from the sun travel in a perfectly straight line until they lit something.
And if they don't hit your eye, you don't see them.
You see nothing. So unless you're looking directly at a star or a planet or the moon, there is no light coming at you from the sides. It is absolute profound blackness, even if the sun is blazing right next to you.
It's the absence of a canvas to paint on.
That's a beautiful way to put it. And that lack of a canvas, that lack of air, leads to the next extreme, which is temperature.
Okay.
The source material uses a really vivid term for how spacecraft had to deal with this. They call it the barbecue roll.
The barbecue roll. I highlighted this. It sounds delicious, but I assume it's for survival.
It is absolutely essential engineering.
Yeah.
And to understand it, we have to understand heat transfer. On Earth, if you stand in the shade on a hot day, you don't instantly freeze. Why is that?
Because the air around you is still warm. It touches you.
Right. Convection and conduction. The air molecules physically touch your skin and transfer their heat to you. In a vacuum, there is no air. So convection and conduction don't exist. The only way to move heat around is through radiation, which is basically light.
So it's all or nothing. You're either in the light or you're not.
It is completely binary. The side of the spacecraft facing the sun is absorbing raw, unfiltered solar radiation. It gets boiling hot. We're talking 250 degrees Fahrenheit or more.
So hotter than boiling water.
Oh, yeah. Meanwhile, the side in the shadow, it's staring out into the blackness of space, which is near absolute zero. So it's radiating its own heat out into the void and getting absolutely nothing back. It drops to minus 250 degrees.
That is a 500-degree temperature difference across the width of a single spaceship. That sounds like a recipe for metal just snapping.
It is. It's called thermal stress. It would warp the frame, it would crack the electronics, it would destroy the vehicle.
Yeah.
So the solution is the barbecue roll. They simply rotate the spacecraft very, very slowly.
Just like a rotisserie chicken.
Just like a rotisserie chicken. You toast one side for a little bit, then you turn it into the dark to cool off, which brings the cold side into the light to warm up. It just evens out the temperature so the ship doesn't melt on one side and shatter on the other.
It's such a low-tech, almost elegant solution to such a high-tech problem. The answer is just spin it.
Sometimes the simplest physics dictates the solution.
Yeah.
You just have to work with what you've got.
This brings us to the darker question. The source addresses this, and I think every sci-fi movie has its own version of the answer. What happens if you step outside? No suit, just you, in jeans and a t-shirt, in the void.
The movies almost always get this wrong. It's a huge trope. You see people freezing instantly, turning into a solid ice statue, and then shattering.
Right, like they got dipped in liquid nitrogen.
That wouldn't happen. Remember what we just said about the vacuum? It's a fantastic insulator. A thermos flask keeps your coffee hot for hours because it has a vacuum layer inside its walls. Heat can't escape easily.
You wouldn't freeze.
Not instantly. Your body heat has nowhere to go. You would eventually freeze, of course, but it would take hours. That's not what kills you.
Okay, so freezing isn't the killer. Is it the pressure difference, the whole exploding head thing?
It is the lack of pressure. That is the immediate killer. We live at sea level under about 14.7 pounds per square inch of pressure. Our bodies are designed to push back against that weight of the air. When you take that external pressure away, the gases inside your body expand.
So, the bends, like a scuba diver coming up too
It
fast?
bends on steroids. But it's worse than that. Liquids boil at lower temperatures when the pressure drops. At zero pressure, the boiling point of water drops to below your own body temperature.
Wait, you mean my blood?
Your saliva would boil on your tongue, the moisture on the surface of your eyes would boil away, and yes, eventually the water in your blood would start to form gas bubbles. It's a horrifying process called ebullition.
That is deeply horrifying.
It is, but the source is very specific here. You wouldn't explode like a bomb. Your skin is actually remarkably tough. You'd swell up. You'd inflate to about twice your normal size. But the real instantaneous killer is oxygen.
Okay.
In your lungs, the gas exchange relies on pressure. In a vacuum, that whole process reverses. Instead of your blood absorbing oxygen from your lungs, the vacuum of space actively sucks the oxygen out of your blood through your lungs.
So you suffocate instantly.
You have about 10 to 15 seconds of useful consciousness. That's the time it takes for that deoxygenated blood from your lungs to travel to your brain.
10 seconds.
10 seconds to realize you've made a terrible, terrible mistake and try to get back to the airlock. After that, you pass out. The source says if someone could drag you back inside within about 90 seconds, you might survive with some nasty bruising and temporary blindness. Any longer than that, and you're gone.
So space is a place where you boil, swell, and suffocate simultaneously, all while one side of you burns like an oven and the other freezes solid.
Welcome to the cosmos. It's not a friendly place for biology.
Okay, let's zoom out. We've established that space is, surprisingly close, just 62 miles up, but absolutely deadly. Now I want to talk about scale. Because space, a visual encyclopedia, really tries to hammer home just how big the neighborhood is. And again, our human intuition just fails us here.
It does. Our brains aren't built for these kinds of numbers. They become meaningless.
So let's try to break it down using time and analogies as our measuring sticks. Let's start with the moon, our closest neighbor.
The moon is so deceptive. It hangs up there in the sky. It looks like it's just right there. You can see craters and mountains with a decent pair of binoculars. It feels reachable.
But the source throws some numbers at us. It's 240,000 miles away.
Which, again, is just a number. It's hard to visualize. So let's put it in terms we can understand. If you were driving a car at a steady 70 miles per hour nonstop, it would take you nearly 6 months of driving to get there.
6 months behind the wheel, 24 hours a day. And the Apollo astronauts, who were in the fastest vehicles of their time,
it took them 3 full days. 3 days of coasting through absolute nothingness just to make that first jump. And here's a metric I love. Light. Light is the absolute speed limit of the universe. It can circle the Earth 7 times in a single second.
blindingly fast.
It still takes light 1.3 seconds to get from the Earth to the moon. That's why there was that awkward delay in the audio during the moon landings. You'd hear Neil Armstrong say something, and then there was that pause. Houston. Pause. The Eagle has landed. That's the light speed delay.
And in terms of size, the source says you could fit about 50 moons inside the Earth.
Roughly, yeah. But here's the visualization from the book that always gets me. You know all the other planets in our solar system. Mercury, Venus, Mars, Jupiter, Saturn. All of them.
The whole family, yeah.
You can fit every single one of those planets in the gap between the Earth and the moon.
No, you can't. Jupiter's huge.
It fits. With thousands of miles to spare. Saturn with its rings, Jupiter, all of them, they all fit in that space. That tells you how much empty space there is just in that first hop to our own satellite.
That is deeply unsettling. It's not a neighborhood, it's a desert. And that's just the very first step. Then we go out to the solar system proper.
And the scale just jumps exponentially. The source mentions the Voyager probes. Voyager 1 and 2, they launched back in 1977.
Right.
They are some of the fastest objects humans have ever built. They're traveling at nearly 40,000 miles per hour right now.
A rifle bullet is slow compared to Voyager.
Not even in the same league.
Yeah.
And yet, it took Voyager 12 years just to reach Neptune, the last major planet in our solar system.
12 years at 40,000 miles an hour.
Imagine getting on a bus, and the bus doesn't stop, doesn't slow down for 12 years. That's the scale of our own backyard.
And once you leave the backyard, once you cross the orbit of Neptune...
Then you are in the deep ocean, the space between the stars. The nearest star to us, Proxima Centauri, is about 4.2 light years away.
Okay, let's define light year again, because we use it so casually, and it's a ridiculous distance.
It is. A light year is a measure of distance, not time. It's the distance that light travels in 1 year. That's roughly 5.9 trillion miles.
Trillion.
So 4.2 light years means that light traveling at 186,000 miles per second takes more than 4 years to get from there to here. If that Voyager probe we just talked about tried to go to the nearest star, do you know how long it would take?
I am scared to guess.
About 70,000 years.
70,000 years. So all of human recorded history is just a blip compared to the travel time to the next house on the block.
That is exactly right. And that brings us out to the scale of the galaxy, the Milky Way.
Which is our, our home city of stars.
It is a vast spiral city, about 100,000 light years from one side to the other.
100,000. The numbers just stop meaning anything.
You do. So the source uses an analogy here that I think is vital for perspective. Imagine an alien civilization is out there, and they're scanning the galaxy. They decide to fly through the Milky Way. Would they even notice Earth?
Well, we like to think so. We've been broadcasting I Love Lucy in radio waves for a century. Surely they'd see us.
But the galaxy contains, on the low end, about 100 billion stars. Some estimates go up to 400 billion.
400 billion.
To an alien explorer just passing through, Earth is a tiny speck of dust, circling one utterly average yellow star in a sea of billions upon billions of others. Unless they knew exactly where to look, we are statistically invisible. A needle in a continent-sized haystack.
That is a crushing thought.
Or a very liberating one, depending on your perspective.
And the Milky Way isn't alone, is it? It's not the only city.
No, not at all. We're part of a small cluster of galaxies we call the local group. Our nearest major neighbor, the Andromeda Galaxy, is 2.5 million light years away. The light we see from it tonight left before modern humans existed.
So when we look at Andromeda, we're looking millions of years into the past.
You're always looking into the past. And looking even further, the source tries to wrap its head around the total number of stars in the visible universe.
This is where the numbers just break my brain. I can't even process it.
The estimate they give is 10,000 billion stars.
That's not a number, that's just noise. My brain just hears a lot.
The visualization is much better. There are more stars in the observable universe than there are grains of sand on all the beaches on Earth combined.
Wow.
Think of every beach you've ever been on, every desert, every handful of sand you've ever held. Every single one of those tiny grains is a sun, and most of them probably have planets.
That really frames the introduction of the book differently. When they say small blue planet, they are not kidding. We are not even a grain of sand.
We are subatomic in the grand scheme of things.
So this brings up the obvious question. If we are so impossibly small, and the universe is so mind-bogglingly big, and we are stuck on this one rock, how in the world did we figure all this out? We didn't have Voyager for 99.9% of human history.
This is my favorite part of the story, Section 3. The history of observation. It's a detective story that spans millennia.
It really is. I think we have this tendency to look back at ancient people and think they were simple. They believed in a flat earth, they were just wandering around confused, but the source material completely corrects that record.
Ancient people lacked our technology, not our intelligence. They were incredibly observant, maybe more so than us, because the sky was their calendar, their clock, and their navigation system. Their survival depended on it.
Let's talk about that flat earth idea. It's weirdly popular on the internet again, but the text points out that we knew the earth was round thousands of years ago. The ancient Greeks knew.
We did. You didn't need a rocket. You just had to look at the evidence that was right in front of you.
So what were the smoking guns for around Earth?
Well, the first one was the lunar eclipse. When the Earth passes between the sun and the moon, we cast a shadow on the moon's surface. Aristotle noticed this back in 350 BCE. That shadow is always curved. It's always a piece of a circle. Now, a flat disk could cast a curved shadow from one angle, but if you look at it from the side, it would cast a line. Only a sphere casts a perfectly curved shadow every single time, no matter the angle.
It's just pure geometry. It's undeniable.
Undeniable. Then there was the evidence from sailors. As you travel north or south for long distances, the sky changes. If you sail from Greece down to Egypt, you start to see stars on the southern horizon that you could never see from home.
And the North Star gets lower in the sky.
Exactly. If the Earth were a flat plane, everyone would look up and see the exact same dome of stars. The only explanation for the changing sky is that you are moving along a curved surface, which changes your viewing angle.
And the classic one, the ship sailing over the horizon.
Classic proof. A ship sailing away from you doesn't just get smaller and smaller until it's a dot. It sinks. The hull disappears first, then the deck, then the sails, until finally the top of the mast is gone. It's dropping over the physical curvature of the Earth.
So we knew the shape of our world, but we got our position in the universe completely wrong. The whole center of the universe problem.
This was a much harder nut to crack, because on this one, your senses actively lie to you.
Right. I mean, I'm sitting here, I'll feel like I'm moving at 1,000 miles an hour. If I drop a pen, it falls straight down, not backward.
And you look up, and you see the sun rise in the east and set in the west. The stars rotate around the North Star every night. The logical, empirical conclusion based on what your senses tell you is, I am stationary, and the heavens are spinning around me. It's a very reasonable model.
So what broke that model? What was the glitch in the matrix that they couldn't explain?
The planets, specifically Mars.
Mars again. It keeps coming up.
It's the key. The word planet comes from the Greek for wanderer. The stars were fixed on a spinning sphere. They all moved together. But Mars, Jupiter, and Saturn, they roamed among the stars. And sometimes they did something that seemed impossible. They moved backward.
Retrograde motion.
Exactly. Mars would be moving across the sky night after night from west to east against the background stars. Then it would slow down, stop, move backward for a few weeks, stop again, and then resume moving forward.
Like it was doing a little loop-de-loop in the sky.
And if Earth is the stationary center of everything, that motion is a complete nightmare to explain mathematically. Ancient astronomers like Ptolemy had to invent these incredibly complex systems of epicycles, circles on top of circles, to try to make the math work. It was a mess.
Enter the game changers. The source lists a guy named Hipparchus first.
Hipparchus is the unsung hero of ancient astronomy. We're talking 2nd century BCE. He didn't just look, he measured everything. He cataloged over 850 stars by brightness. He realized the Earth precesses. It wobbles like a top over thousands of years.
Wow.
But most impressively, he used the geometry of a lunar eclipse to calculate the distance to the moon. He was off by a bit, but he was in the right ballpark. With no telescope, no computer, just sticks, shadows, and math.
But the big paradigm shift, the one everyone knows, was Copernicus.
Copernicus, the man who basically stopped the sun and made the Earth move. He proposed heliocentrism, a sun-centered model.
Why, though? Was it just a guess, or did he have new evidence?
It wasn't about new evidence. It was about simplicity and elegance. He realized that if you put the sun in the middle and have Earth orbiting it in a smaller, faster orbit than Mars, the retrograde motion explains itself perfectly.
Explain that. How does it work?
Imagine you are driving a fast car on a multi-lane highway. That's Earth in the inner lane. There's a slower truck in the outer lane. That's Mars. As you approach the truck from behind, it looks like it's moving forward against the distant scenery.
Okay.
But right as you overtake it for a moment, the truck appears to move backward relative to the trees in the far distance.
It's an illusion, a parallax effect.
Exactly. Mars isn't actually moving backward in its orbit. We're just lapping it on the inside track. Copernicus showed that the loop was an illusion caused by our own motion. It was a radically simpler explanation.
But his model wasn't perfect, right? The source notes that his predictions for where the planets would be, they still didn't quite line up with observations.
Because he was still trapped by one piece of ancient Greek philosophy. He believed that the heavens were perfect, so orbits had to be perfect circles.
And they're not.
They are not. And that's where Johannes Kepler comes in. Kepler was the man who trusted the data more than the philosophy. He looked at the meticulous, decades-long observations of Mars again, always Mars, and realized this path is not a circle. It's slightly squashed. It's an oval.
An ellipse.
An ellipse. And once he switched the shape of the orbits from perfect circles to ellipses, the math became perfect. The planet's positions could be predicted with absolute precision. He'd finally solved the code of the solar system.
And once we knew how they moved, we became obsessed with seeing them better. We needed better eyes. Which leads us to section 4, the tools of the trade, the telescope.
The telescope changed us from passive observers to active explorers of the cosmos.
But the source tracks a really interesting evolution here. It's a constant battle against gravity and our own atmosphere.
It really is. A telescope is basically a light bucket. The bigger the bucket, the mirror, the more light you can catch from faint, distant objects. So for centuries, the goal was simple. Just build bigger mirrors.
Until we hit a wall, a physical limit. The Hale telescope at Palomar.
Palomar Observatory, 1948. A 200-inch mirror. That's 16 feet across. A single massive slab of Pyrex glass. It was an absolute marvel of engineering, but it was also pretty much the limit.
Why? Why couldn't we just make a 20-foot one?
Because glass is heavy. It's technically a very slow-moving liquid. If you try to make a solid mirror much bigger than 5 or 6 meters, it starts to sag and deform under its own weight.
It warps.
It warps. Even a tiny microscopic warp will distort the starlight and give you a blurry image. We simply couldn't build bigger single-piece glass eyes. We were stuck.
So how did we solve it? The source points to the Keck telescopes in Hawaii as the next big leap.
2 incredible innovations. First, segmentation. Instead of trying to make one giant, impossibly heavy sheet of glass, they used 36 smaller hexagonal mirrors that fit together perfectly, like a honeycomb.
Like tiles on a bathroom floor.
Exactly. Each segment is much lighter and easier to support, but the second innovation is the real magic. It's called adaptive optics.
I need you to unpack this because the text mentions these mirrors actively changing their shape 2,000 times a second. That sounds like science fiction.
It basically is. It's designed to solve the other great enemy of astronomers.
Yeah.
Our own atmosphere. The air above us is turbulent. Hot air rises, cold air sinks. There are wind currents. That turbulence bends and distorts the light from stars as it passes through. That's why stars appear to twinkle.
Which is romantic if you're writing a poem, but terrible for science.
It's terrible for science. It blurs the image and smudges out all the fine detail. So adaptive optics uses a brilliant trick. They shoot a powerful sodium laser beam up into the sky, right next to the star or galaxy they want to look at.
What does the laser do?
It excites a layer of sodium atoms left over from meteorites in the upper atmosphere, and it creates a tiny glowing dot, a fake artificial star.
A guide
A
star.
perfect guide star. The computer knows exactly what that laser dot should look like, a perfect point of light. But of course, the atmosphere distorts it on its way back down. The computer measures that distortion, calculates exactly how the air is bending the light in real time, and then sends commands to hundreds of tiny pistons under each of those 36 mirror segments.
And the mirror flexes.
It flexes. It warps itself into the exact opposite shape of the atmospheric distortion. It pre-corrects the error, it cancels out the blur, and it does this 2,000 times every second.
It's like noise-canceling headphones, but for light.
That is the perfect analogy. It takes a blurry, twinkling star and turns it into a sharp, steady pinprick. It allows a ground-based telescope to take pictures that are almost as sharp as the Hubble Space Telescope.
That is absolutely incredible. And then the source mentions the VLT in Chile, the Very Large Telescope.
Astronomers are very literal with their names.
They really are. And the VLT uses a different trick called interferometry. What's that about?
This gets a little complex, but think of it this way. The ultimate resolution, the amount of fine detail you can see, depends on how wide your telescope is. The VLT is actually 4 separate large telescopes spaced out over a distance.
Okay.
But they have a system of underground, vacuum-sealed tunnels with mirrors that bounce the light collected by all 4 scopes and combine it perfectly in a central laboratory.
So they act as one giant single telescope.
They simulate a mirror that is as wide as the distance between the outermost telescopes. It's called increasing the baseline. It doesn't give you a brighter image, but it allows you to see incredibly fine detail, like spotting the individual stars in another galaxy.
And the future. The source talks about the EELT.
The European Extremely Large Telescope.
Of course it is.
This is what's currently being built in Chile. It will have a segmented mirror that is 39 meters wide. It's over 120 feet. Compare that to the 16 feet of the Hale telescope. It will gather 15 times more light than any telescope we have today. We're going to be able to see the atmospheres of Earth-sized planets around other stars and look for signs of life.
Now, speaking of seeing amazing things, I want to talk about one specific image from the source that just blew my mind. The light echo of a star called V838 Monocerotis.
Ah, V838 Monocerotis. Yes. This is one of the most beautiful and counterintuitive sequences of images that Hubble ever took.
Describe it for us, because when I looked at the photos, which were taken over several months, it looks like a classic explosion. You see this
Yeah.
red ball of gas and dust just getting bigger and bigger, expanding outward at an impossible speed.
It looks exactly like that, and it seems to be expanding faster than the speed of light, which we know is impossible. What happened was, back in 2002, this red supergent star suddenly flared up. It became 600,000 times brighter than our sun for a short period.
Like a giant flashbulb went off in the middle of a dark room.
That is the perfect way to think of it. And that flash of light creates this visual of a red sphere expanding outward. But nothing is actually moving outward at all except the light itself.
Okay, so if matter isn't moving that fast, what are we actually seeing?
Imagine you are standing in the middle of a massive, pitch-black cathedral. The air is full of ancient, invisible dust and smoke. You have a powerful flashlight. You click it on for just 1 second, then click it off.
A pulse of light shoots out.
Right. That pulse travels away from you at the speed of light. First, it hits the pillars 10 feet away from you, and for a moment, you see those pillars light up. Then, a fraction of a second later, the pulse hits the pews 50 feet away, and they light up. Then the back wall of the cathedral lights up.
So if I'm watching from the entrance, it looks like a ring of light is just growing outward, painting the invisible structure of the cathedral as it goes.
Precisely. The star, V838 Monocerotis, is surrounded by vast, ancient shells of dust that it ejected long ago. They were invisible. When the star flashed, that light pulse traveled outward. First, it lit up the closed dust. Then, a month later, it was illuminating dust that was a light month away. We are watching a three-dimensional scan of the surrounding neighborhood as the light wave washes over it. It's not an explosion, it's an echo made of light.
That is hauntingly beautiful. Okay, so we've looked at the universe, we've built these giant glass eyes to measure it, but looking isn't enough. We want to go there. Which brings us to section 5, leaving Earth.
This is where we leave the realm of optics and enter the realm of brute force and controlled explosions.
Because gravity is a jealous ex. It does not want to let us go.
It really doesn't. The physics of launching a rocket are brutal. To get into a stable orbit, just to stay up there, you need to hit 17,500 miles per hour, sideways.
And if you want to leave entirely, to go to Mars or the moon,
Then you need to achieve escape velocity.
Mhm.
For Earth, that's about 25,000 miles per hour.
I want to circle back to orbit, though, because the source explains weightlessness in a way that finally clicked for me. I think most people, myself included, assume that when you see astronauts floating in the International Space Station, it's because there is no gravity up there.
It's a very common misconception. At the altitude of the space station, about 250 miles up, gravity is still about 90% as strong as it is on the ground.
Yeah.
If you could build a tower that high and stand on it, you'd feel almost your normal weight
So why are they floating? What's going on?
because they are falling,
Falling.
constantly falling. Imagine you're on top of that tower and you throw a baseball. It curves down and hits the ground. Now throw it faster. It goes further before hitting the ground. Now imagine you have a superpowered arm and you can throw that ball at 17,500 miles per hour.
Okay, Superman arm. Got it.
The ball still curves down toward the ground due to gravity. But because the Earth is a sphere, the ground curves away underneath the ball at the exact same rate. The ball is falling forever, but it keeps missing the surface. That's what an orbit is.
So astronauts are in a permanent state of free fall.
Yes. That feeling you get in your stomach when a roller coaster drops over a big hill, they feel that 24 hours a day, 7 days a week. That feeling is weightlessness.
That sounds absolutely nauseating.
It is at first. It's called space adaptation syndrome. Most astronauts spend their first few days being very, very sick.
Now, to get that kind of speed, 17,500 mile per hour, you need a massive rocket. And you can't just launch a rocket from anywhere. The source outlines the location rules of spaceports.
There is a very clear strategy to where we build spaceports. You can't just put one in downtown Chicago.
What are the big rules?
Rule number 1 is safety. Rockets are basically controlled bombs filled with millions of pounds of explosive fuel. If they fail, and they sometimes do, you want them falling on uninhabited land or preferably open water.
Makes perfect sense.
Rule number 2 is you have to launch east,
Why always east?
because the Earth spins towards the east. If you are standing on the equator, you are already moving at about 1,000 miles per hour to the east just by standing still.
So if you launch east, you get a free running start from the planet itself.
Exactly. It's free velocity. It saves an enormous amount of fuel.
Hmm.
If you launched west, you'd have to fight against the Earth's rotation, which would be incredibly wasteful.
In rule 3, you want to be as close to the equator as possible.
Because the spin is fastest there. The further north or south you go from the equator, the slower the surface speed is. It's like being on a merry-go-round. The person on the outer edge is moving much faster than the person near the center.
So let's look at the spaceports mentioned in the book, Cape Canaveral in the U.S.
Florida. It's a pretty good location. It's on a swampy coast, so it launches east over the Atlantic Ocean, which checks the safety box. And it's relatively far south in the U.S., so it gets a decent speed boost.
But the source says the European Space Agency actually has an even better spot, Kourou.
Kourou, in French Guiana, South America. It is arguably the best launch site on the entire planet. It's almost right on the equator. They get a huge velocity boost compared to launching from Florida or Russia.
Speaking of Russia, Baikonur Cosmodrome.
The legendary site in Kazakhstan. It's where Sputnik launched, where Yuri Gagarin became the first man in space. It's totally landlocked, so they launch east over the vast empty steppes of Central Asia for safety.
But the Russian list has a really weird one, Plesetsk.
Plesetsk. This one breaks the equator rule completely. It is located near the Arctic Circle.
Why on earth would you launch from the Arctic? You lose almost all of that speed boost from the planet's spin.
Because it was a secret military site. The Soviets wanted to launch spy satellites into polar orbits that go north to south over the poles so they can scan the entire surface of the Earth as it rotates beneath them. For that specific type of orbit, being far north is actually helpful. And the thick forests provided excellent cover. They didn't even officially admit the site existed until 1983.
The secret spaceport in the woods. And finally, the most extreme and clever engineering solution, sea launch.
The Odyssey platform. This is just brilliant. It's an old self-propelled oil rig that was converted into a mobile launch pad. They sail it out to the middle of the Pacific Ocean, park it exactly on the equator at 0 degrees latitude, and launch from there.
It's genius. If you can't build a permanent base on the equator, just bring the base to the equator.
Precisely. You get the absolute maximum boost from Earth's rotation.
So we have the rockets, we have the speed, we are breaking escape velocity. Where are we going? The source focuses very heavily on one particular destination, Mars.
The red planet. Our great obsession.
Why are we so obsessed with Mars? I mean, why not Venus? It's closer and about the same size as Earth.
Because Venus is a literal hell.
Yeah.
The surface pressure will crush you, and the temperature is hot enough to melt lead.
Mm-hmm.
Mars is, well, it's extremely difficult, but it feels familiar. The source highlights the similarities. A day on Mars is 24 hours and 37 minutes long, almost exactly an Earth day.
So you wouldn't get jet lag?
Pretty much.
Yeah.
And it has an axial tilt like Earth, so it has seasons. It has polar ice caps made of both water ice and frozen carbon dioxide.
It feels like a cousin planet.
A ruined cousin, maybe. A ghost of a world that might have once been like ours.
Let's talk about the visual. Why is it the red planet?
The redness tells a fascinating chemical story. The surface is covered in iron oxide, which is just rust. But the presence of so much rust implies that something crucial was once there that is mostly missing now.
Oxygen. You can't get rust without oxygen.
And water. Oxidation happens much faster in the presence of moisture. So the surface of Mars is essentially a fossil. It's a record of a time billions of years ago when Mars had a thicker, oxygen-rich atmosphere and liquid water on its surface. The iron in the rocks reacted with that environment, turning the whole planet red before the atmosphere was stripped away by the solar wind.
So it's not just a red planet, it's a rusted planet. It's a corpse.
That is a very accurate, if grim, analogy.
And the geography there is just... it's extreme. Mars doesn't do things halfway. Let's start with the volcano, Olympus Mons.
The largest volcano in the entire solar system. It beggars belief.
How big are we talking?
The base of the volcano is 375 miles wide. That would cover the entire state of Arizona or the country of France.
Yeah.
And it is 16 miles high. That is 3 times the height of Mount Everest.
How did it get so gigantic? Earth volcanoes don't get anywhere near that big.
Plate tectonics. Or rather, the lack of them on Mars. On Earth, our crust is broken into plates that move. A volcanic hotspot punches through the crust, builds a mountain, but then the plate moves on and the volcano goes dormant. A new one forms over the hotspot. That's how you get the Hawaiian island chain, a series of volcanoes.
But on Mars...
the crust never moved. The hotspot just sat in one place for hundreds of millions of years, pumping out lava, building one single monster stack of rock.
And the canyon system, Valles Marineris.
A scar across the face of the planet. It's 2,500 miles long. On Earth, that was stretched from New York City all the way to Los Angeles. It makes our Grand Canyon look like a scratch in the driveway. It's so big that if you were standing on one rim, you wouldn't even be able to see the other side because of the planet's curvature.
So visually, it's a stunning world. but as a place for humans to go.
It's lethal. Utterly lethal.
Let's start with the atmosphere.
It's about 100 times thinner than Earth's. The pressure is so low it's almost a vacuum. And what little air there is, it's 95% carbon dioxide. You'd suffocate instantly without a suit.
And the weather. The source goes into detail about the dust storms.
These aren't just little dust devils like you see in Arizona. Every few years, Mars experiences a global dust storm. A storm starts in one region and just grows and grows until it covers the entire planet. The sun is completely blocked out. The whole globe becomes a fuzzy, featureless orange ball for months on end.
And that dust isn't like beach sand, is it?
No, not at all. On Earth, water and wind action smooth out sand grains over millions of years. On Mars, the dust is finely ground volcanic rock. It's sharp, it's jagged, and it's highly abrasive. And it's also electrostatic. It clings to everything. Solar panels, spacesuit joints, machinery. It's an engineering nightmare.
And we can't forget its moons, Phobos and Deimos.
They're not majestic round orbs like our moon.
Mhm.
The source calls them potato-shaped, which is perfect.
Just lumpy potatoes floating in space.
They're tiny. Phobos, the larger one, is only about 14 miles across. They're almost certainly captured asteroids, rocks that were wandering through the solar system, got too close to Mars, and were snagged by its gravity,
Kidnapped asteroids.
essentially. And poor Phobos is doomed. Its orbit is decaying. It's spiraling inward toward the planet. In about 50 million years, Martian gravity will tear it apart and turn it into a spectacular ring system,
Space is violent, even for the moon.
especially for the small moons.
So let's try to bring this all home. We have gone from the thin air of the exosphere, looked at the incredible engineering of giant mirror telescopes launched from a floating rig in the Pacific, and toured the rusty Grand Canyons of Mars. It is a lot to process.
It is, absolutely.
But what is the takeaway from all this? Why does this matter to someone who is, just driving to work right now?
I think it goes right back to that introduction in the source. It alludes to the pale blue dot sentiment that Carl Sagan made so famous. When you truly internalize the scale, when you realize that the vast distance to the moon is just a short hop and that our entire galaxy is one of billions, it fundamentally changes how you see our own world.
It makes us feel incredibly small.
Small, yes, but also incredibly fragile and rare. We've looked at Mars, a dead, rusty, frozen world. We've looked at the vacuum of space, a place that boils your blood. And then we look back at Earth. This thin, delicate, wet biosphere is the only place in the entire universe so far that we know for certain we can survive.
It's a lifeboat in an impossibly vast ocean.
It's the only lifeboat we have.
Yeah.
And all 7 billion of us are in it together.
And there's one final thought from the source that I want to leave our listeners with. It's a provocative question. We talked about the visible universe being 93 billion light years across, but the source asks a simpler, bigger question. How big is the universe?
And the answer is the most exciting phrase in all of science. We don't know.
We really don't. There's no theory.
There are theories, but we don't know. We cannot see an edge. We don't even know if there is an edge. The universe could be infinite. What we see, that 93 billion light-year sphere, is just our observable bubble. It's the region of space from which light has had enough time to reach us since the Big Bang, 13.8 billion years ago.
So beyond that bubble, there could be more.
There could be more universe. There could be an infinite amount of universe filled with an infinite number of galaxies, stretching on forever.
An infinite dark ocean. And we're just seeing the little circle illuminated by our flashlight.
That's exactly it. We have barely scratched the surface.
On that incredible, humbling note, I want to encourage you to do one thing tonight. Just step outside, get away from the city lights if you can, and just look up. The night sky isn't just a ceiling, it's a time machine. Every point of light you see is a piece of history.
And you're looking at physics, at chemistry, and ultimately, you're looking at home.
Thanks for diving deep with us. We'll see you on the next journey.
Keep looking up.